All right, we're ready. So Friday's quiz, this coming Friday's quiz in 2 days, is going to cover most, not all, but most of the lecture material that we've been doing with the skeletal system with bones. Then next Tuesday will be quiz number 4. And what quiz number 4 will cover will be whatever we don't get to on the skeletal system, on the bones and joints. So quiz 3 will be all skeletal system up to probably some point through tomorrow's online lecture / meeting. And then the following quiz will cover the last bit of the skeletal system / bones and joints. So that's what to expect on quizzes 3 and 4. Quiz 3 in particular, and possibly quiz 4, maybe a few more questions than 30, maybe closer to 30, between 35 and 40, because there's more detail, there's just more information as we go through the organ systems in A and P. All right, so where we left off yesterday, we got pretty far, which is good. We described what compact bone tissue looked like under a microscope and the functionality of the cells in that, and we went through the language. Really quick review, we went through the language of what an osteon is, a osteocyte living in a lacuna, what a lamella ring is, it's layers of bone matrix, a canaliculi, a central canal. So those structures and that vocabulary you should be familiar with from yesterday's lecture. Today I'm going to start off talking about directly comparing spongy bone tissue structure. We already finished compact bone tissue structure. So I will pull up my whiteboard. Just let me do that real quickly. So share content, whiteboard, here we go. So I'm just gonna quickly, it's difficult for me to write legibly, I know, sorry about that, on this vertical glassy surface with a pen, but I do my best. So I'm just writing spongy bone structure. You know most of this already from what we've done up to this point. I might just layer on a little tiny bit of detail. So you know already that in the end of a long bone or in the middle of a flat bone, we have these little tiny bone needles or spicules or struts. It almost looks, if we were to look at a dead bone, a bone from a person who has already died, it would look like these little tiny bone needles with air spaces in there. But in life, when we are alive, those spaces are not filled with air. They're filled with red marrow and capillaries. So what I'm doing is I'm going to magnify that spongy bone structure and draw these really big. Now these are tiny in real life. These are little tiny bone needles that branch like this, and they're sort of interwoven between each other. So I'm drawing, and the name for these little needles, these little bone needles or spicules, is trabeculi. And I'll write that out. So these are called, the actual bone in spongy bone is these little needles. That's Trabeculae. That's plural with an E. If I take the E off the end of that, that means I'm talking about one little piece. So the actual bone tissue are trabeculi, and the spaces between the trabeculi, it's not airspace. There's this, I'm going to pull up a different color. I'm just going to use yellow for this sort of gel-like, it's not fat, it's a gel-like structure, gelatinous structure where we have stem cells, those osteogenic cells, as well as hematopoietic cells. So more importantly, in this yellow bone marrow stuff, and I'll label that, I was going to use red. This is actually called red bone marrow. The reason I'm not going to use red is because there's also capillaries, blood vessels, meandering through this stuff as well. So these are capillaries, small blood vessels that I'm drawing now that also run. So I'm drawing, this whole picture that I'm drawing is just an example of what spongy bone actually is. So I'll label this just a capillary. A capillary is just the smallest type of blood vessel in the human body, and it allows things to go in and out of the blood because it's so small and thin. So let me put an arrow on that. So we've got capillaries, red bone marrow in the spaces of trabeculi. Now in trabeculi, we still have living bone cells. So I'm going to draw a lacuna, these little cavities or spaces called lacunae, and they are found in the bone tissue, and they have living osteocytes in them, okay? And I'm going to put a little black dot in each little cavity, and what that represents is a living bone cell inside of a lacuna. I'll label that. Osteocyte in a lacuna. Lacuna just is, remember, is the cavity or cave that the osteocyte lives in or resides in. An osteocyte would be a, osteo means bone, cyte means mature cell. So it's a mature bone cell. That's basically the last thing that I'm going to do is cover these trabeculi, and it's hard for me to do on a two-dimensional surface, but I'm just going to put a blue line sort of on the surface of these trabeculi, because these trabeculi are covered with a thin, delicate connective tissue. It's the same stuff that lines the medullary cavity in a long bone. It's endosteum, or we say endosteal tissue. So I'll move over here. Endosteum is a thin, delicate connective tissue that lines the medullary cavity. It also covers trabeculi in spongy bone. Just cover one more of them. And that's a pretty accurate big view of what spongy bone really looks like. It's made up of these bone trabeculi, the spicules, the needles, and it looks like they're randomly arranged. They're not. Physiologically, these trabeculi are arranged so that they resist stress on the bone. So just like building a bridge or something, the girders that stabilize a bridge that we drive over in our cars, those are all engineered and arranged so that they resist stress. Same with these little tiny bone needles called trabeculi. So we've got trabeculi, we've got red bone marrow in the spaces of the trabeculi. And what's in red marrow? I'm just going to remind you that I don't have enough space to write this big word. Hematopoietic tissue. That means it makes our blood cells. That's where our blood cells are synthesized or created. Red blood cells, white blood cells, and platelets. And there's capillaries in this network. And finally, there is endosteum covering the trabeculi. This osteocyte, so we still have osteocytes living in these pockets or caves or lacuna. And believe it or not, they do have these little tiny canals running from lacuna to lacuna, so these osteocytes can communicate with each other. So we do have osteocytes in lacuna. I'm just going to put with canaliculi. But as you can see, unlike compact bone, there's no osteon or growth ring type of arrangement. There's no unit of bone growth in these trabeculi. All right, if you want to screenshot that, go ahead. Don't worry, I'm recording it. If you don't want to screenshot it, and I will post a recording later today. I am going to move on with my whiteboard and talk about something new. Next topic is about ossification. So in order, it's just a fancy word for a very simple meaning. I'm going to write calcification. It's imperative that you understand the difference between these two words, calcification and ossification. Calcification, as the name implies, refers to the depositing of calcium in a particular area or tissue. Sometimes books say laying down of calcium. I'll tell you what that means. We have calcium in our bloodstream. Most of our calcium is stored in our bones, but we have what calcium we can use at any given moment is found in the blood. And the word calcification just means blood taking calcium to a certain area and depositing it into a tissue or a certain area. So that's what the word calcification means. Ossification literally means the formation of bone tissue. These two terms are closely related, but they're not identical, okay? We need calcification as a major ingredient for ossification to occur. I'll say that again. Calcification, the depositing of calcium, is a major ingredient for this process to actually occur. So we can't make new bone without calcium being deposited into the area where we want to make new bone. There are other ingredients, though, that need to happen for true ossification to occur. So just think of, if ossification is baking a cake, cracking and whipping up eggs would be an ingredient, a major ingredient. That would be an analogy to calcification. You can't make cake without eggs. So that's sort of the analogy I'm trying to make here. Now, I am going to talk about the next major topic in your book is embryonic ossification. What this topic refers to is how our skeleton is formed when we are still in utero, when we're still developing in the uterus as an embryo. And that's what that means. There's two different types, and I'm going to briefly go over them. There's a lot more detail in your book than I have time to go over in this meeting, and I'm going to expect you to know the major points of this for your quiz, but you don't have to know all of the details. And I'll try to hit the major points today. So there's two types of embryonic ossification. The first one is called, I'll get a new board when I go over these individually, but I just want to talk about endochondral ossification is the first one. And we're going to, first thing to do is to define these words, what they mean. We know what ossification means now. It means the formation of bone tissue, or in this case, the formation of the skeleton. Endo means within. Chondral means cartilage. So what endochondral ossification literally means is the developing of bone or skeleton within a cartilage model. I'll describe this process now on my next whiteboard, okay? So I'm just going to delete this one and move on. And I'm just going to give you a few details about endochondral ossification. I teach a 200 level of A&P as well at Camden County and at Rowan University. And those students, I require to know much more detail about this process. With my basic A&P students, I want to hit the major point. So we know what the word means. It means that developing a bone or skeleton within a cartilage model. These are the bones, the specific bones of the human body that use this process. And in this case, it's all bones. It's easier to write it this way, except the clavicle, which is the collarbone, the clavicle and bones of the cranium, cranial bones, I'll put in parentheses skull. So all bones in the human body use this process to embryonically or embryologically develop, except for cranial bones of the skull and the clavicle, the collarbones. That's step one. Now here's what's, I'm not gonna list out every single detail of the steps like your book does. The reason is because that's all I'd have time to do today and I need to get going. Plus I'm not gonna have you know every little bit of detail. And basically here's what happens. We start with a cartilage model. So if you were to look at somebody in utero while they're developing embryologically, you can see if we do an ultrasound, for example, on a baby developing in the mother's uterus, you can see some sort of a skeleton start to develop. Technically, really, that is hyaline cartilage. So hyaline cartilage is the type of tissue, the type of cartilage tissue that's used as the model for this type of development. And then a skeleton, a bony skeleton, develops from that hyaline cartilage. So let me write that. A bone skeleton develops from a hyaline cartilage, that's a C, a hyaline cartilage model. So when you look at an ultrasound of a baby developing the mother's uterus, and you see what looks like a skeleton developing, technically that's just a hyaline cartilage. So these little cartoon bones, they are actually made not of bone, but of hyaline cartilage. There's certain ingredients we need for ossification to occur. And this is basically what we need. We need a blood supply that brings nutrition and calcium to the area. That's an and sign. Brings nutrition and calcium. So we have to have a blood supply. We have to have calcium in the area. Calcification occurs. So I'll write that in parentheses. That was our first word of the day. That's why we say calcification is a major ingredient for ossification. And we need osteoblasts in the area. Because remember, osteoblasts, those immature bone cells, they secrete that gooey stuff, that organic material called osteoid, that you can just say mixes with calcium. It incorporates the calcium into the osteoid is technically what it does. To ossify or to form bone. And if you know those two steps, what you read in your textbook will then sort of make sense. I know it's difficult reading sometimes, but your book goes through step one, a bone collar forms around the diaphysis of a hyaline cartilage model, blood vessels infiltrate. So, step one in your book says blood vessels infiltrate this area. That's because that's a requirement. It's a major ingredient. So remember, this is a hyaline cartilage model. We're in development in the mother's uterus. Blood vessels start to invade this area, the diaphysis, the shaft of this little hyaline cartilage cartoon bone. A periosteum develops. I'm just going to use green. We know what a periosteum is now. That starts to develop in this area. And then what are called, don't worry about this, but mesenchymal cells, those are just embryonic connective tissue cells that give rise to all different types of connective tissues. In this case, we're making bone. So embryonic mesenchymal cells invade this area and they differentiate into osteoblasts. So osteoblasts, those immature bone cells, let me get back to black here, they develop in this area as well. So we're just basically detailing step 1 and step 2. Once we have blood supply, we get nutrition and, more importantly, calcium to that area. Once we have osteoblasts, now we have the cells that can secrete this organic osteoid and mix with the calcium to actually form bone tissue. So there's other steps that occur during this process. The old cartilage cells that make up this bone, they enlarge and die. They blow up and sort of enlarge and die, and they leave a space in this area that is the beginning of the medullary cavity, that space in the shaft of a long bone. And then eventually these osteoblasts secrete osteoid, they mix with the calcium deposited by the blood, and we get actual bone forming. Now, the last thing I'm going to write over here is that almost always, when we have new bone tissue developing, spongy bone develops before compact bone. So spongy bone, when we're making new bone, spongy bone almost always develops first. And then if the area requires compact bone tissue, the spongy bone in that area gets converted to compact bone. All right, so that's a really quick but important basic lecture on endochondral ossification. Now I'm going to switch to the second type of embryonic ossification. So I'll save this board in case you need me to go back to it and just layer over the top of it. The second type of embryonic ossification is called intramembranous ossification. It's a big word that it's not that difficult to understand. I'll decipher it for you. So just like we did the last time, we know what ossification means. That means the formation of new bone or a skeleton. Intra means also within. Membranous just means membranes. So we're not going to start with a hyaline cartilage model first. We're going to start with fibrous connective tissue. So I'll write that in parentheses. And you know now what bones exactly use this process to develop embryologically. And so this only bones of the skull and the clavicles are our collarbones use this process to develop. So we have a skeleton developing within fibrous connective tissue membranes, all right? So we've deciphered what this means, and we know which bones use this process. So I'm just the basics here. Rather than a hyaline cartilage model, we don't use that in this particular form of development. We start out with a sort of a bird's nest, a mass of fibrous connective tissue. So I'm just going to draw that. I'm just going to write fibrous CT. That's what we're starting with. There are mesenchymal cells. Those are those embryonic connective tissue cells in this mass of tissue. I'm going to repeat this. Mesenchymal cells are just embryonic connective tissue cells. So every single type of connective tissue that you went over with our last unit, all those connective tissue propers, meaning loose, dense, all cartilage, all bone, all fluid connective tissue, basically are developed from these basic cells when we are embryos. All right, so we've got fibrous connective tissue with mesenchymal cells, okay? And ossification centers appear in this fibrous connective tissue. What that means is these mesenchymal cells differentiate into osteoblasts. So we get a mesenchymal cell that just from chemical signals in the body from development, they develop into osteoblasts. So I'll label this. We know that we need osteoblasts as a major ingredient to make bone tissue. Also, blood vessels invade this area. And guess what? That's going to bring nutrition and calcium to the area. So this is, ossification almost always occurs in a similar fashion, meaning we need blood vessels to bring the nutrition and calcium, and we need osteoblasts to secrete that organic matrix. Now we have osteoblasts, now we have blood vessels bringing nutrition and calcium to the area, so that the osteoblasts, I'll draw one, let me erase that. I'll draw an osteoblast over here. It's secreting osteoid, that sort of gooey bone, organic bone stuff. And then the blood vessels are bringing calcium to the area, and the osteoid mixes with the calcium to form hard bone tissue. All right? That is how the bones of the skull and clavicles develop. The biggest difference, guys, is what we start with, the blank canvas. With endochondral ossification that we went over first, we start with a hyaline cartilage miniature bone model. With intramembranous ossification, we start with just fibrous, dense fibrous connective tissue. That's the biggest difference. The process of ossification is basically the same. Osteoblasts secrete osteoid, blood vessels bring calcium and nutrition, they mix to form hard bone tissue, and remember, spongy bone, I'll rewrite this again, spongy bone typically develops first, and if we need compact bone, so I'm going to write then, compact bone develops from spongy bone. So that is like 3 or 4 pages in your textbook. And those are the basics and the information that I'm going to expect you to at least be able to know for our quiz, okay? Now I'm going to go over, hopefully we'll have time, I should have plenty of time to do this, 2 types of bone growth in the human body. So I'll layer on a new whiteboard. Let me add one here. First type of bone growth that we're going to look at is, I'll write 1, growth in length. How does a long bone grow longer when we are children and when we're going through puberty in our teens? That's what this topic is about, okay? How long bones grow in length. You've heard of a growth plate. That's what we're going to examine here in great detail, okay? So growth occurs at a growth plate. I want you to know this scientific term. A growth plate is scientifically called the epiphyseal plate. Remember, epiphysis just means the end of a long bone. So that's where this word comes from. Epiphyseal plate is the same thing as a growth plate. What is it? It's made up of hyaline cartilage. Technically, it's in the metaphysis area between the diaphysis and the epiphysis. So I'm just writing this language out for you so you have a handle. Remember, diaphysis means the shaft of a long bone, and epiphysis is the end. So in the area, in the collar area, right between the shaft and the end, the diaphysis and the epiphysis, is a cartilage plate, a hyaline cartilage plate called the epiphyseal plate, all right? That just gives you an idea of what we're talking about. Now I'm gonna erase this board and really draw out the detail of a growth plate. And I'll label all of the language and structures that I'll expect you to know for a quiz, okay? So if I draw, I'm gonna go way up here and draw the epiphysis of a long bone. Then I'm gonna use blue to signify that there's a cartilage plate here, and I'm gonna elongate it. I'm gonna really exaggerate it, okay? It's usually not this long. The reason is because I have to draw different zones of growth. Now I'm gonna draw the shaft or the diaphysis of the long bone. So there we are, we're a child, or let's just say we're 12, 13 years old. And our bones are still growing in length because we're still growing in size. This is what we have. We have the epiphysis of the bone up here. That means the end. We have the epiphyseal plate here, the growth plate, which is made up of hyaline cartilage. And we have a diaphysis, or the shaft of the bone. So if you were to x-ray a child's bone, a long bone, like in the arm, leg, even in the fingers or toes, you would see something like this on a single bone. Now, here's what happens. At the epiphyseal plate, up here at the top, close to the epiphysis, there's something called the quiet zone. Don't worry, I'll label all this business. And the quiet zone is butted up against the actual end of the bone right here, all right? So high activity of the growth plate actually occurs lower down in this area. And I'm gonna erase those X's, and I'm gonna label these zones of the growth plate and define them for you. So here we go. Up here at the top, we call this zone 1. And it's known as the quiet zone. And the reason it's called the quiet zone is because remember, this is cartilage. All of this thing is cartilage. And in the quiet zone, we have no new, I'm going to put in parentheses, cartilage growth activity. Chondroblasts, which are immature cartilage cells, they do the growing of new cartilage. While right here in the quiet zone, there's pretty much nothing going on. It's just a quiet cartilage plate. But in the next zone, number 2, you know what, I can make that a little bit thicker. So in the second zone, number 2, That's the opposite. This is called the proliferative zone. And we have a high cartilage growth activity. So I'm going to write high chondroblast, that means immature cartilage cell, activity, period, new cartilage growth. So let's say we're talking about a child that's anywhere, I don't know, from, it doesn't matter, from 8 to 12 years old. Their growth plate, their epiphyseal plate, a lot of new cartilage is being laid down in zone 2, and it pushes upward on the quiet zone like this. And that pushes the epiphysis up and away from the growth plate like this. So the first thing we're describing is the growth plate itself is pushing up on the epiphysis of the bone. And rather than the growth plate just keep getting bigger and bigger and longer, what's going to happen is the growth plate down here is going to dissolve, and literally bone is going to end up eating away at the old part of the growth plate. And the growth plate itself is just going to keep pushing up this way, and that's how the bone is going to grow. So let's just, I'm going to label, let me erase these. I'll leave them there. Zone 3. So we've got the quiet zone, proliferative zone. The next area is called the hyper. It's a big word, but it's not hard to understand. That's H-Y-P-E-R. Hyper. This is all in your book if you can't read my writing. Hypertrophic zone. This is where old cartilage cells enlarge and die. Okay, so the hypertrophic zone, so we've got new cartilage in the proliferative zone pushing upward. And then behind that zone are older cartilage cells, and what they do is they literally blow up like a balloon, and they sort of pop, they die, leaving spaces or cavities in this area. So I'm just going to draw that. So old cartilage cells enlarge and die in zone 3. Zone 4, right here, is called the calcification zone, and you know what that word means now. In the calcification zone, there are old cartilage dead cells, dead cartilage cells, and blood vessels invade this area and bring calcium to it. So I'm going to draw some vessels going in here. So let me get my black pen back. Sorry, it's pollen in the air. Can't speak very well. So I'm just going to write blood vessels invade the area. You know what's coming next. They bring calcium. I'm going to write Ca++ because that's the short for calcium ion. They bring calcium, and they lay it down. Calcium is laid down in that old cartilage area. So this is why it's called the calcification zone. Finally, the last area, number 5, is not in the growth plate itself. It's in the diaphysis of the bone. And that's the ossification zone. So in the ossification zone, that word, you know now, it means the formation of new bone tissue. In the ossification zone, we have a high osteoblast activity. And new bone formation. And literally, these osteoblasts here are laying down osteoid, combining with the calcium found here. And if you were to watch in real time a growth plate, if you could sort of time lapse a young person's growth plate, we get pushing up here and gobbling up of the old cartilage plate and laying down of new bone down here in the ossification zone. And that growth plate just keeps making new stuff here and old cartilage gets replaced by bone down here. So the diaphysis is getting longer in bone. Meanwhile, the epiphyseal plate in the epiphysis keeps getting pushed further upward. And it's at the end of puberty, at the end of our growth spurt, here's what happens. I can't write this down because I don't have any room to do it. Hormones are secreted in the body at the end of puberty that tell this new cartilage growth in the proliferative zone to stop. So mostly it's estrogens that are released in both males and females in mass during the end of puberty. And when that occurs, our growth plates seal up, they close. And what that estrogen does is it tells this proliferative zone of the growth plate to stop making new cartilage. But these osteoblasts keep chugging along, gobbling up old cartilage. And what happens is this new bone eventually seals up this cartilage plate so that the diaphysis seals up with bone to bone at the end of our growth spurt. And that's when we're done growing. And it's estrogen that actually signals the process of the sealing of our growth plates. All right, that was a big topic, I know. The last topic of the day is not going to be quite as detailed. I'll save this board and layer on top. That was long bone growth and length. The last topic for the day is apositional bone growth. And that's not quite as detailed. This means the growth of a bone in width, not in length. That's supposed to be, sorry about the writing, it's hard for me to do this. In width. So I'm going to say some things as I draw this picture. So let's just say we have a bone. I'm going to draw a bone. There it is. There's the medullary cavity in the center of the diaphysis of that bone. So this is compact bone here. This is the medullary cavity. In an infant, it's filled with red marrow. In an adult, it's filled with adipose tissue, yellow marrow. All right. Now, how does this bone grow in width? Basically, it's an ongoing process as we're growing. Osteoblasts beneath the periosteum. So I'm going to draw I'll use green for this. So if this is a periosteum covering the diaphysis of this bone, osteoblasts, immature bone cells that lay down new bone matrix right here, they secrete osteoid and mix with calcium to make the bone thicker. That's pretty easy to understand. So the first step is osteoblasts beneath the periosteum secrete bone matrix on the external surface, right? So the bone gets thicker as osteoclasts, and I'll just use a different color for those cells. Let's just use red. Osteoclasts on the endosteal surface, the medullary cavity endosteal surface in here, they dissolve bone. So what we end up getting is, however, I'm going to say one more thing before I draw my next picture. So we've got high osteoblast activity here, aka new bone is being laid down. And we've got high osteoclast activity on the inside, where old bone is being dissolved or eroded away. And what that presents is something that ends up looking like this. The bone gets thicker because of the osteoblast activity, and the medullary cavity gets wider because of the osteoclast activity. Now, typically in apositional growth, the osteoblast activity outpaces osteoclast activity, so that, yes, as the bone thickens totally in width, the medullary cavity gets bigger, but bone tissue gets more thick than the medullary cavity, if that makes sense. So we get a thickness to the bone. The compact bone area keeps getting thicker and thicker. And even though this medullary cavity is getting larger in diameter, the osteoblast activity is faster. So this bone keeps getting thicker and thicker like this. That's called apositional bone growth. And bone remodeling, once we are fully grown, so this occurs, apositional bone growth, when we're young, as well as longitudinal or bone growth and length while we're young, which we went over with the epiphyseal plate. Now, after we are fully grown, after we finish our growth spurts, we're in our 20s, and for the rest of our lives, our bones are not static. That osteoblast and osteoclast activity does not stop. We do have continued for the rest of our lives something called bone remodeling. This term refers to the constant osteoblast and osteoclast activity throughout life. Okay, so in adults like you and me, our bones are not static. There's new bone constantly being laid down where needed, and old bone being eroded away. And so our bones are constantly undergoing some sort of remodeling process, even though, and this activity is relatively the same as this activity, so that our bones don't really grow or shrink in length until we get really old. And we're approaching a term called osteoporosis, but let me first say one more thing about bone remodeling. During this time, osteoblast activity rate is relatively equal to osteoclast dissolving rate, so the bone doesn't change that very much in size. So we're constantly making new bone and getting rid of old bone, but the bone doesn't overall change inside because the rate of activity of these two things is about the same. When we're growing, osteoblast activity is faster than osteoclast activity. And when we get old, so you've heard of osteoporosis, but this term getting ahead of myself. Osteopenia, you might not have heard of. I will quiz you on this term. Osteopenia is the normal or typical thinning of bone tissue. So osteoblast activity, this means new bone. This means dissolving old bone. And during bone remodeling, when we are fully grown, these two rates are the same. When we're growing, when we're young, osteoblast activity is higher or faster than osteoclast activity. When we're adults, say from at the end of our growth spurts, our late teens through, say, our mid-50s, for women, it occurs upon menopause, what I'm getting into next. So when we're young, this is worth noting. So when we're young, osteoblast activity is faster than osteoclast. That's why our bones grow. When we're adults, we still have bone remodeling. That means these activities are about the same. So we're still making new bone and getting rid of old bone, but at the same rate. So it doesn't matter, our bones stay about the same size. When we get older, that's what this topic refers to. And this osteopenia term refers to the normal thinning of bone due to the slowing down of osteoblast activity. So as we age, and this is hormonally regulated, as we age, when we get to midlife or past midlife, say in our 50s, osteoblast activity slows down. Osteoclast activity, unfortunately, keeps chugging right along. The dissolving or the removing of old bone tissue, so I'm just writing osteoclast activity remains at the same rate or pace. Therefore, you can guess what happens. Our bones start to get thinner as we age. Osteopenia refers to that typical thinning of bone tissue. Osteoporosis, which is what you've heard of. Osteoporosis is actually a condition, and I'm going to say it's an extreme. It's normal for, in almost all of us, our bones to get a bit thinner as we age. Osteoporosis actually refers to the extreme condition of osteopenia, in which our bones get so thin that the structural integrity of our bones is compromised. What that means is that they crack and break. That they can fracture, break. Somehow the structural integrity is compromised so much that we're in danger of fractures and breaks. That's what osteoporosis refers to. And just to give you an idea of what happens in the body to both males and females. Females, unfortunately, suffer from lack of ossification, proper ossification, more than men do. I'm just going to go to a new page here. I'm still talking about osteopenia and osteoporosis. Women can lose up to 8% of bone mass per decade. And that's usually after menopause. So I'm just going to put after their 40s. Typically women, it's different for each woman, but typically they go through menopause late 40s through their late 50s, anywhere in that time period. So upon the onset of menopause, and especially after menopause, women are at risk of losing up to 8% of their bone mass per decade. That's a lot. You think, geez, in three decades, they could lose 24% of their bone mass. Men are still at risk, but not quite as much as women. And the reason is because it's estrogen related. After women go through menopause, their estrogen levels decrease much more so than in men. And men's bodies are less dependent on the estrogen to begin with. So men can lose up to about, that's what that sign means, about 3%. So they're still at risk of losing bone mass, just not quite as much per decade after their 40s. So I'm going to tell you something. Physical stress, some degree of physical stress on bones is healthy. Obviously not too much stress or our bones break. But when we are young, or even and when we're not so young, our tendons, I'm going to draw a bone here. Let's just say this is the femur, the upper leg bone. We have muscles that attach, hip muscles and leg muscles that attach via tendons all over this area of our upper leg bone, the femur. So here's a muscle attaching to the bone. When this muscle contracts, every time we take a step, we walk, we jump, we climb stairs, whatever, it pulls on the bone. You know that. So this muscle contracts, it pulls the bone this way. The physical stress of the muscle pulling on the bone at that attachment point, it causes new bone to grow in that area. So here's what happens during muscular physical stress on bone. I'm just going to write first, we get stress, and I don't mean stress from being in a car accident. Obviously that's going to break a bone. I mean stress from doing physical activity. So stress causes the minerals in that area of the bone to be energized. It increases the mineral activity, the electrical activity. So when a muscle pulls on a bone in that area, the electrical activity of the minerals in the bone right here increases. That attracts osteoblasts to that area. So the increase in mineral electrical activity of a stressed bone area attracts osteoblasts to the area. And you know what osteoblasts do now? The osteoblasts, they secrete new bone matrix. They secrete osteoid, which mixes with calcium being brought in from the blood to make new bone, which is called ossification. So you can see in people who are athletically active, physically active people, they have protrusions on their bones where the muscles attach. And the more active that person is, the bigger that bump becomes. The less active that person is physically, the smaller that bump becomes because they have less bone there. So I always tell students this, think about that the next time you take the elevator up one flight of stairs. It's much healthier for your bones if you just walk up that flight of stairs, because that causes your muscles to pull in this area and actually create new bone tissue. So some stress, physical stress on bones is healthy, is a good thing. All right, I'm going to leave you with that. I'm going to stop recording now, and then I'll take questions, okay? So just let me hit.